So our next speaker is Anita Vuchkovska, and she is R&D chemist at WR Meadows, and she is developing new polymer-based materials, and she was my master student, and she worked on the dispersion of nanomaterials, nanoparticles for application in polymeric coatings and treatment of concrete and masonry. And Anita, let's start with your presentation.
Hello everyone. Dr. Sobolov already gave a presentation on the importance of nanotechnology and how it has revolutionized different scopes in various industries. However, even though it has done remarkable things in the biotechnology, medicine, and targeted drug therapies, it has not reached its full potential in the construction and the building industry. One reason is the difficulty of dispersing and the agglomeration of the nanoparticles, and therefore achieving the large surface area and associated benefits with it. I work as a chemist, as Dr. Sobolov said, and one of the difficulties that we have is the incorporation, and I think Dr. McFarlane was talking about that, the incorporation of the nanoparticles in composite or polymers, because they tend to agglomerate. The large nanoparticles are thermodynamically unstable, and therefore they will be most stable when they're in a colloid system, when they're completely separated into different phases. So in order to stabilize them, we either have to increase the repulsive forces between the nanoparticles or to reduce the attraction forces, the van der Waals forces between the particles. For this presentation, we are going to provide some information on the on this presentation. We will be talking specifically for the nanotitanium dispersions that can be further utilized as precursors in coating and other composites, cementitious composites. So when we talk about stability of colloidal nanoparticles, we are really looking into the colloidal stability, but also the gravitational stability. So the colloidal stability, it refers to the particle size change over time. If there is no particle size change, we have achieved good colloidal stability. However, the gravitational stability plays a huge role when we are talking about the stability of the overall system, especially in coatings or other systems. So from Stokes' law, we can see that the force of the particle that needs to move through a viscous liquid is directly proportional through the velocity and the density of the particles. There is a schematic representation that's basically showing on the right side that if we don't have a stable system, aggregates or agglomerates and flocculates and aggregates will form, and then they will eventually sediment. On the right side, it shows the degradation mechanism if we don't have the proper gravitational stability. Now, many times you can hear that you can achieve a colloidal stability even if you have gravitational instability, which is correct for a certain period of time. However, over time, if you have a concentrated amount of particles in a small space, they will start to flocculate and eventually they will coalesce and aggregate, and then you will get the phase separation. When we talk about stability, we talk about mechanical stability and we talk about chemical stability. Sonication has been a proven method about mechanical stability of nanoparticles. However, I also want to mention when we talk about powder pigments that besides sonication, the wetting out of the pigments play a crucial role. Sonication, it's not sufficient to wet out the titanium dioxide nanoparticles. The other is the chemical stabilization. When we talk about chemical, there is electrostatic stabilization, steric stabilization, or electrosteric stabilization, which is a combination of the first two. Steric stabilization refers primarily to it's also known as polymeric stabilization or nanionic stabilization, when nanionic surfactants are used, and usually polymers get absorbed on the surface of the particle and the repulsive forces are formed. The electrostatic stabilization, which will be the focus in our presentation, it's typically when you're using anionic surfactants and something known as double layer forms around the particle. As the particle moves a small part of the liquid moves with the particle. The place where the shear plane is basically the edge layer, and this is where we are calculating the zeta potential, which is the measure of the electrostatic repulsive forces. In this study, we have chosen to work with the Evonik Aeroxide titanium dioxide P25 particles, which is 3:1, anatase to rutile crystal grade. It's 35 to 65 square meter per gram particle size area. The surfactant, two surfactant that we have chosen to work with is the Dow TMO731DP and the BASF Dispex CX4910. The first one is a sodium salt of polyacrylic acid, and the second one is a sodium salt of polyacrylic acid. We have intentionally chosen to work with those two commercially available surfactants. The first one is commonly used surfactant for dispersion of inorganic pigments, but it's also used among variety in many different coatings. The second surfactant, it's used more as a dispersant in dried powder materials. So it would be something like grouts and other cementitious materials. This is our design of experiment, our DOE, and initially we have started with something that is very agglomerated, and we were striving to achieve something that it's a monodispersed system, something that have a uniformity of 0 or polydispersity of 0, but we very well know that something with polydispersity of 0 is very rarely seen. If anything, you might see something like that or close to that in the biotech world. So in reality, what we really were getting, it's something more that you get like more agglomerates. And photos from the SEM on the left side are showing that we have started with something that is very agglomerated, and we have created dispersions. That even though they have been dispersed, there are still some agglomerates. As we already mentioned earlier, that the sonication is very crucial, and it's a known method of dispersing the nanoparticles. Our studies have also shown that by just high shearing or using a rotor stator homogenizer for dispersing of the nanotitania particles, it was not an effective method, and the size of the particle was reduced by half just by utilizing the sonication method as per the DOE in the previous slide. And this is also supported by the polydispersity or the uniformity of the particle size sample. So we were also using different wetting processes or different techniques. We started with a rotor stator homogenizer, and even though this was not a problem, this method was not a problem if you're just dispersing the titanium dioxide nanoparticles, it became a huge problem when we were working with the surfactants. The anionic surfactants are foam, so when you're using very high shearing, you create a lot of foam. That it's a very stable foam, and it's something that it's not wanted, especially in the coatings. So we decided to try something that have a lower energy, something like a propeller blade mixer, just to see if the wetting out method, as long as following with sonication, will be sufficient for that. And from the studies, we can see there was no significant difference whether you will use a rotor stator homogenizer or a propeller mixer, as long as sonication will follow right after. And this was supported by both the polydispersity and the particle size. And you can see that we have done the particle size and polydispersity at 3 days and 30 days, and there was not a significant increase. So even though the particle size was not necessarily less than 100 nanometers, it is still a system that was dispersed, and the overall stability of the material was there. Those are some of the material characterizations for the different formulations that we have done. So the stability, this is visual, and it's primarily for the gravitational stability. The first tube, it's representative of samples that have been stable, and majority of the formulations with exception to the formulations that were not sonicated have shown stability, as in the first tube. The second and the third tube are representative of the samples that were not sonicated. So shortly after we were done with the mixing or with the homogenation, the phase separation will start, and you will get a complete phase separation or sedimentation. At the beginning, when you have sedimentation, you can use mixing or other or sonication or other methods where you can bring back, if you have agglomeration, you can bring back the material in that you can stabilize the dispersion. However, as time progresses and goes over time, you form more aggregates, and this becomes very difficult to disperse afterwards. The pH was tested for ASTM E70. This is just a glass electrode test method. And the reason I bring this up is that it's something very simple step, but it's very frequently overlooked. It's very important when you're formulating into coatings and with the dispersions itself, because the pH the pH can tell us a lot of about the materials. So, for example, if you can see it in the first one where there is no surfactant, there was not significant difference between the samples, and the reason everything is the same. It's just the method of producing. The Tamil 731 DP in the samples where it was used. So the blue lines are representative of 1% titanium dioxide samples, and the red lines are of 2% titanium dioxide. In the first, you can see a trend where the pH is being reduced as the amount of titanium dioxide is increased. This is indicative that the surfactants is getting absorbed at the surface of the particles. Similar at the Dispex CX4910, however, not to the degree as with the Tamil, we see a similar trend, only here it's reversed. The pH increases slightly as the amount of titanium dioxide increases. Density per D1475 was also measured, and this is also just to check a lot of times for us to make sure that there is any issues with our it's a checkpoint. So you have theoretical points, and this is just an actual measure to show. And as we expected, density for the 2%, it's supposed 2% suspension or dispersions it's higher than the 1%. Oops, wrong way. Furthermore, we measured the particle size, and we used the dynamic light scattering, and we did it 3 and 30 days for all the samples except the samples that were not sonicated. We have seen a particle size somewhere roughly around like 170, 180 to like 190, and we have measured the particle size between 3 days and 30 days, and there was not a significant increase in particle size. And also the first sample is showing that there is not like a significant increase in particle size. However, what is the benefit of using a nano powder titanium dioxide if you have 350 nanometer particle size, when the bulk material of titanium dioxide is somewhere around there? So you don't get the benefits of the surface area and the surface energy of the material. The polydispersity at 3 and at 30 days was also measured, and there was not a significant difference between the two. One thing I want to mention is because we didn't have the polydispersity refers to the non-uniformity. So because we didn't have a monodispersed system, we had a polydispersed narrow system, when typically a polydispersed narrow system is between polydispersity 0.1 and 0.4. Below 0.1, it's a monodispersed, narrow monodispersity. You can see on some of the graphs that we have slight reduction or slight increase on the polydispersity, and this is when you're running the samples. If you have agglomerates in the sample, even though they're properly dispersed, sometimes when you're testing, you might grab like something that has like slightly larger than other, which could lead toward some of the results what we are seeing here. And the zeta potential was the last thing that we were measuring, which is basically the electrostatic repulsive forces. It's a measure of the electrostatic repulsive forces. If no surfactant was used, we get like a positive zeta potential, and with the surfactants, we got a negative zeta potential. Zeta potential, it's a very important check, when you're trying to do electrostatic stabilization. However, many people rely just on the zeta potential, and zeta potential on its own, it's not sufficient. If you take a look at the first sample without sonication, we saw pictures that this sample is not stable because there was a lot of sedimentation. However, we still get a zeta potential of 35. So really, when we are working about the stability of those materials, it's an overall thing that we need to look at multiple things. One other thing that the reason why we were using different surfactants and we were trying to achieve different pHs. So as you're working with coatings or with cementitious materials and you're trying to incorporate those nanoparticles, you want to get, you don't want to hurt. You want to make sure that your nanoparticles are stable, but you also need to make sure that the systems where you're incorporating those nanoparticles are not affected by the interactions. So for example, if you will incorporate like titanium dioxide in a coating, since titanium dioxide or the specific grade we are using decomposes organic matters, you will have to incorporate into something that has inorganic content, something like a silicone coating. And in this case, you need to ensure that the emulsion, or the silicone emulsion, will not be also, the stability will not be jeopardized by the nanoparticles that will be incorporated in it. From our studies, we could conclude that the mechanical energy, homogenation, or mixing is not sufficient to develop stable dispersions. As many other studies have shown, the homogenation or mixing used to wet out the nanoparticles is insignificant when ultrasonic waves are used subsequently. There was no significant difference in particle size and polydispersity between formulas with and without surfactant. And there is no significant increase in particle size and polydispersity from 3 to 30 days. The zeta potential was greater than 30 millivolts, indicating good or moderate stability. Typically, when we work with the zeta potential, one other thing I wanted to mention is that the electrophoretic measure is very, we also need to establish where the pH at which the zeta potential will be 0, because at that pH there is no any repulsive forces. So it is a very, so for different materials it will be different. For example, something like silica, it can have a very, you can get a very stable system at a lower zeta potential, but for something like titanium dioxide, you probably need somewhere above 50 or even 60 millivolts plus or minus absolute to get something in a stable solution, or like nano dispersions. And some of the applications and importance and use of this one, the wide range of pH opens opportunity and flexibility for the use of materials in different applications, such as coatings, stucco, plasters, concrete, and film composites. I also want to say thank you to Professor Sobolev, the Sobolev Research Group, and the Advanced Analytical Facility.